Why is probability amplitude essential to quantum mechanics? Imagine trying to predict where a tiny particle might be or how it might behave. In classical physics, you can often give exact answers. But in quantum mechanics, things are more mysterious. Instead of definite outcomes, we deal with chances and possibilities. That's where probability amplitude comes into play. It's a special kind of number that helps us understand these probabilities. The concept of probability amplitude became a key part of quantum physics in the year 1926. Max Born proposed that the wave function, which describes a quantum system, should be seen as a probability amplitude. This idea changed how scientists predicted what might happen when they measure particles like electrons or photons. Instead of saying exactly where a particle is, they could now calculate the likelihood of finding it in a certain spot. This shift from predicting fixed results to probabilities was a big step forward in understanding the principles of matter and energy. Probability amplitude is a complex number, meaning it has two parts, magnitude and phase. The magnitude tells us how likely something is to happen, while the phase influences how different quantum states combine. This phase aspect leads to interference effects, which are unique to quantum physics. For example, in the famous double-slit experiment, particles like electrons create interference patterns that look like waves. These patterns happen because the probability amplitudes of different paths add together, sometimes reinforcing each other and sometimes canceling out. This wave-like behavior is something classical physics can't explain, and it shows how important probability amplitude is for describing quantum phenomena. Mathematically, quantum states are represented as vectors in a special space called Hilbert space. The probability amplitude is found by taking the inner product of these vectors. This mathematical operation links the abstract description of a quantum system to real-world measurements. It allows scientists to calculate the chances of a particle transitioning from one state to another or scattering in a certain way. These calculations are the foundation for many quantum technologies, like quantum computers and secure communication systems. Without probability amplitude, we wouldn't be able to connect the math of quantum theory with what we observe in experiments. It's the key to understanding how quantum systems evolve and interact. It also explains why particles can behave both like particles and waves, depending on how we look at them. This idea of probabilities and complex numbers has opened up new ways to control and manipulate matter and energy at the smallest scales. In essence, probability amplitude is the bridge that turns the abstract language of quantum mechanics into real, measurable predictions. It helps us understand the strange and fascinating world of quantum physics, where outcomes are not set in stone but are shaped by the interplay of probabilities. This concept has driven many scientific discoveries and technological advances and remains a central part of how we understand the universe at its most fundamental level.